welcome to the Axis Splinter session. And so we're going to tell you three main things. The first thing is we're going to just tell you about some exciting science we think you can do with high spatial resolution, wide field of view, X-ray imaging and spectroscopy. And then the second thing will be telling you more about the Axis mission, about the demirs, about the detectors. And then finally, we really want to get community involvement. So we're going to tell you how to get involved. I'm sure there's someone in this room or online that has some really good ideas that we haven't thought about. So we want to get you guys involved and everyone in the room involved. So our first speaker will be Erin Cara, who's going to give an overview of the exciting science and her particular expertise of looking at the transient universe. So go ahead, Erin.
Okay. Thanks, Mike. All right, thanks everyone. I'm going to take my mask off. Yeah, so I'm going to be giving you a brief overview of Axis. I think probably if you're willing to stay this late into the meeting, you probably know a little bit about Axis, but just to recap very quickly, Axis is a high spatial resolution, really great PSF over a wide field of view. That's like the key thing about Axis is that PSF doesn't degrade over the field of view like Chandra does. And so the PSF is going to be really small, out to 28 by 28 arc minute field of view. I'm getting confused by an actual pointer. I haven't used this in a couple of years now. The other thing that's exciting about Axis is that it's a tenfold improvement over Chandra pre-launch in effective area, 3 times the effective area of XMM Newton, and it has fast slew capabilities. That's going to be, all of this is key for the transient science. I'm going to be telling you about it as well. And we'll also hear a lot about the science of that the low background also enables. Okay, so just to again highlight this, we've heard a lot about Astro 2020 in this session, in this meeting. I called for an X-ray probe, and I just want to highlight here that it specifically says in this illustrative figure that this X-ray probe should contribute to the 3 pillars identified by the decadal. So worlds and signs and context, new messages and new horizons, and cosmic ecosystems. And so what I think is really Axis is kind of meeting those requirements set out by the decadal survey. The other thing that Axis that the decadal mentioned specifically is that this probe mission should complement Athena, as I think it does. Okay, so this is just an overview of where we're going in the science section here. So we have Leah Corrales who's going to tell us about worlds and signs and context. Mike, so like cosmic ecosystems is I think a no-brainer for Axis, and we're going to have a lot of science in that pillar. So Mike Koss is going to be telling us about the earliest supermassive black holes and how they evolved over time and through mergers specifically. And Edmund Hodges-Cluck is going to tell us about AGN feedback and galactic feedback as well. And then I'm going to tell you a little bit now about what Axis is going to do for the transient and multi-messenger science. Okay, so I think it's just really important to emphasize that we're in this era of multi-messenger, panchromatic, time domain astronomy. We have a lot of things coming online, both at longer wavelengths, woohoo, and multi-messenger events. But what we're really lacking, there is this X-ray time domain desert in the early 2030s, and this is really what Axis is gonna fill that gap. And this is again to highlight what the decadal has identified as really some of the prime science here. So what I'm highlighting, so there were a bunch of, for those who didn't read through that huge document, there were a bunch of science panels on the decadal, and they each identified like 4 questions, 4 of the biggest questions in their particular field. And what I've put here, I don't expect you to read it all right now, but this is direct quotes from the Astro 2020 decadal survey. And these particular, these are questions that are related to the science of new messengers and new physics. And specifically, I think AXIS can help answer all of these questions. And I won't have time to go into all of the, how we're going to answer all of these questions, but I'm just going to highlight a few. So, of course, multi-messenger astronomy has a lot to do with compact objects. But I think what's really exciting is that this multi-messenger time domain era is also having an effect on cosmology, galaxy evolution, and stars. So in this talk, I'm just going to briefly go through these couple of ones. And I, in particular, want to highlight here the galaxies panel and the compact objects panel both highlighted this question about what are the first black holes, how do supermassive black holes form, and how do they evolve over time. And I think this is like the killer science that AXIS is. You're going to remember AXIS because it's going to do this exciting, like, what's the origin of black holes, how do they evolve over cosmic time, and how do they affect our universe. So first, what powers the diversity of explosive phenomenon? Well, AXIS is going to have that fast slew capability and that really sharp PSF, good sensitivity to follow up transients at a wide range, at a very large volume. And this is just highlighting a bunch of these different, both explosive transients, but also other fast transients. And on the right axis, you're seeing, this is how far AXIS can, the distance out to which AXIS can probe in a 10 kilosecond slewed observation. So we get some event, we're told that we see this event, we slew within a couple of hours, and AXIS can really see out to these very large distances. And just on the right there is a comparison to what SWIFT can currently do right now. So the upshot here is that, Rubin LSST is a 60-fold improvement in sensitivity over ZTF, and AXIS is that equivalent increase in sensitivity for the X-rays. Okay. Next, I'm really excited about binary supermassive black holes recently, and obviously this is going to be one of the prime science of the LISA mission, finding those low frequency gravitational waves from these binary supermassive black holes. And unlike the LIGO detected binary black holes, we really expect that in these gas-rich mergers, you should see an electromagnetic counterpart. These should be bright AGN. Maybe they're going to be obscured, as Mike will tell you more about. And that's even more reason why you're going to need X-ray observations to find the electromagnetic counterpart. And what I want to highlight here is MHD. It's actually just, yeah, it's not, whatever. It's a hydrodynamic simulation of a binary supermassive black hole merger. And while there's a lot of debate in the community on the details of what happens in these systems, what I think everyone pretty much agrees on is that you'll get these mini disks around the binary black holes and a circumbinary disk. And those mini disks are going to be bright in X-rays. So if you're going to look for periodic, whereas like the UV and longer wavelengths is dominated, by the circumbinary disk. So if you're looking for periodic signals from these binary supermassive black holes, the strongest signal is going to be in the X-ray band. And so if we have a sensitive large field of view instrument that can quickly slew and tile those LISA error circles, then we can find the electromagnetic counterpart via X-ray observations. So this is just kind of taking you through our how we're going to actually do this. So LISA should have several events that have like a 1 square degree error circle when they find these mergers, or actually like a month before merger in some cases. And while there will be lots of optical sources in that error circle, there's not going to be as many X-ray sources. And because these systems are AGN, they will be bright in X-rays. We can then kind of focus more on looking at the merging galaxy systems, since these should be the result of galaxy mergers, and use the fact that they're likely to be highly obscured. And then just the upshot is that, you know, this is a kind of a good approach to kind of really be able to isolate what is the binary supermassive black hole candidate, and then you can, you know, use those periodicities to identify the candidate. So you're going to need fast slew sensitivity, because these things are going to happen at like a redshift of 1, and a large field of view to tile quickly. Okay, lastly, this is not something that we really even thought about in our original study to the decadal, but some new exciting science in how does multiplicity affect how stars live and die. This is a slide that Kevin Burge, a postdoc at MIT, put together for me. He's finding all these like ultra compact binaries that are actually going to be like the dominant source of LISA gravitational wave events that from, you know, in our galaxy. And so for instance, like these double white dwarfs, the most compact double white dwarf is actually in X-rays, found in X-rays, and you can see orbital period modulations in X-rays. And also all of the candidate like fun ultra compact binaries that contain neutron stars and black holes, all the really cool ones, are also X-ray sources. So, but what you can see, so like these are expected, you're probably going to see a lot of these LISA events in really dense fields like globular clusters. And this is an example of that one double white dwarf system in a globular cluster. It's a very crowded field. You're going to need high angular resolution to be able to find, to identify what the candidate is. So this is a cool science driver for that fast slew. If LISA finds something, you can tile that very small error circle. It should be like 20 arc minute diameter error circle in these galactic sources. So we can do that, maybe even just one pointing, which would be amazing. And then also you could do timing of the sources in that field to find what is the candidate. So that's all I really wanted to say, but there's so much more that could have been said, and I really encourage you to get involved. So again, I'm just going to flash up that QR code if you want to sign up for our science working groups. And that's it. Thank you.
So do we have any questions anyone wants to ask?
I have a quick one. You talked about fast slew a lot. Are we talking autonomous slewing, or are we talking ground command slewing?
All that I've been saying so far is like when I said a few hours to get on source would be like something. It would be from ground. You know,
Okay,
yeah. We'll talk about things more complicated maybe later on. Yeah, Daniel.
You talk a lot about the synergy with LISA, but even the synergy with Athena is a bit problematic, given that the probe launched 5 years before Athena, and given it 7, 8 years before the launch of LISA.
Yeah, so I have a couple of responses to that. Hopefully, this is a 5-year. Oh, sorry. So the question was about simultaneity with LISA. LISA on their website says it's going to launch in 2034 and whatever. And but what I think is 2 things. So I think there's so much that Axis can do simultaneous with LISA, and I think that will be really exciting in this 5-year mission that we're designing. But the other thing is that like you can do a lot of precursor science as well. So like, you know, looking for periodic signals in supermassive black holes. If you do a scan, you can like find those candidates, and that's going to be really helpful for like nailing down the rates that LISA should be expecting when it does fly. Or for instance, in the case of these compact white dwarf binaries, like if we expect that most of these sources are going to be found in globular clusters, that's like a kind of a not a crazy thing to think. We can do work in advance of LISA flying, and I think we should do just like really deep observations, because there's still going to be periodic 5 years before LISA flies as well. So I think that like and then, you know, LISA will be able to use that we'll find the EM counterpart before we find the gravitational wave counterpart, basically.
Yeah, I mean, I would add too that, there's pulsar timing arrays. There's also, 2 other Chinese and 1 Japanese mission that is trying to detect gravitational waves. So that there's a lot of different parameter space there. Okay, maybe let's go to the next talk. And then we can come back at the end of the science stuff if there are more questions. That's Edmund. Yeah, let me check. Yeah, okay, so. All right, so Edmund is going to tell us about galactic feedback with Axis.
All right, well, thank you all for coming and for postponing your dinner plans. So yeah, I'm going to just talk briefly about the prospects for what we can learn about galactic feedback with Axis and Athena. And I just want, because this question just came up, I want to make clear from the beginning, almost none of this requires simultaneous Axis and Athena. It's the idea of what we get from a high resolution imaging, as well as high resolution spectroscopy and very high throughput science. So, over 20 years, what we've learned from Chandra is a lot about feedback, especially in galaxy clusters. But one of the big questions that was only we only began to answer in the last few years is what about the velocity structure? So with the advent of microcolor motor spectra, the Hitomi-Perseus spectrum, that exquisite spectrum showed us what the turbulence structure is like in the Perseus cluster core that has all of this amazing structure you see with Chandra. And when XRISM launches next year, we're going to continue that very successful partnership. But XRISM, as great as it will be, is really not equipped to dig very deep into feedback on galaxy halo scales. And the reason is because galaxies are smaller, they are cooler, they emit in lines for which the XRISM resolution is worse, and XRISM just doesn't have that much effective area. And even at Chandra at launch, would be unable to produce Perseus quality images for individual galaxies. Yet, we think that feedback in galaxies is extremely important to understanding the way that the universe got to be the way that it looks today. So some open questions are, for example, how does stellar feedback begin in star clusters? Do galactic winds actually regulate star formation in galaxies? Does the CGM have an analogous cooling flow problem in massive galaxies to that seen in galaxy clusters? And how does AGN feedback work from dwarf galaxies all the way up to isolated massive ellipticals? And of course, a lot more. And Axis, the combination of Axis and Athena, are able to answer those questions across the mass scale and across the energy scale of feedback. So when it comes to AGN feedback, for example, on this top row, we can learn about the role of AGN and starburst winds and how they interact and whether or not they have an impact on their galaxies. In more massive galaxies, we can learn about jetted feedback and how that compares in individual galaxies to what we see in galaxy clusters. And then at higher Eddington fraction, we can look at what AGNs are actually doing to their host ISM and how AGN energy is able to regulate ongoing star formation. And in terms of stellar feedback here on the bottom, we can learn about how feedback begins in superstar clusters, map out the energy budget and superbubbles, and finally resolve the origin of various forms of emission and phases and starburst winds, whether they escape their host galaxies and so on. And so you might say, well, why do we need X-rays for this? And I think one big reason is that X-rays trace most of the energy that is contained in these feedback flows. And not only does that energy traced by looking in hot gas, but it's that hot gas that projects and ultimately transforms the mechanical energy of feedback into heat and the processes that regulate star formation. So X-rays really trace this key hidden driver of galaxy growth that Astro 2020 wants us to understand. So just as one example here of AGN in a starburst galaxy, this is NGC 3079, a nearby famous starburst. You can see this nice H alpha filament bubble, super bubble, and what it looks like with Chandra over here on the right. And we know that this bubble is actually associated with the AGN. So the AGN in this galaxy is actually pretty weak compared to the starburst, but this thing is associated with the radio lobe. And so we know that this thing is associated with the AGN. We know the AGN is having an impact on this galaxy, even though there's also a starburst going on. And so what we can learn with the combination of Axis and Athena is, how those things work together by probing the mass, metal, and energy content of these winds. And we can answer questions like, what are the sources of X-ray emission? How do they relate to the other phases that we see? What role do weak AGN play in winds like this? And what is the threshold of AGN power where we get positive instead of negative feedback? And Axis is going to be able to finally resolve the wind structure. To see this, this is a simulation of an Axis observation based on the Chandra plus the H alpha. And you can see that in a relatively short amount of time, Axis is able to measure in exquisite detail the structure of that bubble. And meanwhile, what we get in this one Athena-sized pixel, if you were to take a spectrum from that in a comparable amount of time, is shown here in the spectrum over here on the right. I'm focusing on the oxygen 8 line here. And the point of these plots is to show you that not only can we measure the centroid shift, we can also measure the velocity broadening, because if you don't include the broadening and only the centroid shift, you get poor residuals, as shown at the top right. So the combination of Axis and Athena is really going to tell us, how does this gas, this hot stuff, relate to the cool phases around it, and how is it imparting energy into those phases? In more massive halos, we can understand what is the impact of jetted feedback. And here a big question is, does AGN jetted feedback in elliptical galaxies work similarly to how we think maintenance mode feedback works in massive galaxy clusters? And there's good reasons for thinking the processes might be different. For one thing, you don't need as much energy in order to sustain the so-called feedback cycle. And the conditions for things like precipitation may be different. And the most efficient transport mechanisms by which you get the AGN mechanical energy into heat in the hot gas and so forth may also be different. And so what I'm showing here up at the top left is NGC 4636. It's a Chandra image. And this is a great example. This is a nearby galaxy in the Virgo cluster. It's a great example of where Chandra can actually image kiloparsec scale bubbles, which is about what you would expect if feedback can offset cooling and prevent star formation in these galaxies. But if you go farther away, Chandra simply doesn't get very much signal. And with Axis's exquisite effective area, what we're going to be able to do is increase this sample by more than a factor of 10, probably more closer to a factor of 100, by going out to about 100 megaparsecs away and in fairly modest exposures, finding these kiloparsec scale bubbles. Now, Athena will not be able to resolve these things. So what Axis is doing is it's acting as a finder scope for Athena. It tells Athena where to point, and then you get spectra like the one shown at the right, where you can actually see the expansion of that cavity spectroscopically. At higher Eddington fractions, we can actually start seeing how AGN outflows impacts the ISM of their host galaxies. So this is NGC 3393. It's a Seyfert 1 galaxy fairly nearby. You can see from this HST image, this beautiful S shape or spiral shape in the H alpha and the narrow line region. And then Maxim et al. Went with Chandra and got a very deep image, or a bunch of deep images, and showed that this beautiful image in the center, where you can see that the X-rays more or less follow along with the H alpha. And that's really interesting. Now, what we can do with Axis, which has similar resolution, but much better effective area, is actually start mapping this in individual emission lines. And what that will tell you is, how does the gas at different ionization stages or different temperatures match the phases that we see in the optical or the UV? And that helps us answer questions like, how do the ultra-fast outflows or disk winds connect to the narrow line region? Is the hot gas ionized by the same processes as the warm gas? And how far does AGN feedback extend into the ISM? So in order to see what Athena can do, you actually have to zoom out a little bit. This is a simulation of the exact same galaxy on the previous slide. We're now looking at this region right here, but because we're looking at arc second scales there, we have to zoom out a bit. And if we take an XIFU spectrum from the region right around that S, this is an example of what we would get with Athena. And you can see in this beautifully complex spectrum, this is based on the real Chandra data, and there are lines there that, you cannot fit this with a single zone photoionization or a single temperature plasma. This is wonderfully complex, and by mapping this galaxy in individual emission lines, we're going to learn about how these things relate to each other and where this emission is coming from. So just to summarize, I think that Axis is extremely complementary to Athena, and the combination of those two is really going to revolutionize our understanding of feedback in galaxies and galaxy evolution in a comparable way to what Chandra and Hitomi, and then Prism are going to do for galaxy clusters. Thank you.
Okay, questions?
Please excuse my ignorance. I am very little idea about the process of missions. But between the two presentations, first, it was presented as feeling that it would fill the gap of the 2020's time domain. But now we're talking about synergy again, like working simultaneous maybe with Athena and Axis. So I'm a bit confused in that part. And also one more question too, to maybe anyone who can answer, is that there are things we expect from a mission, and when it's being built, then there are some things that we did not expect and you need to compromise from some things. So do you have your limits on the spectral resolution, like angular resolution, like what is the upper lower limit that you can go, and maybe during the building of the spacecraft actually may have to compromise it? I'm sure Athena had a better idea, better expectations for the spectral angular resolution too, but.
Okay, yeah, so those are both good questions. So if I go back to.
Could you repeat the question?
Oh, yeah, okay. So
Yeah.
she asked two questions. So the first question is, given that we just had a presentation in which Axis was presented as preceding Athena, how does the synergy between Axis and Athena work? And the second question is, what is the limit or what angular resolution makes Axis worth it, if I could paraphrase that question a little bit. So I think, like when I'm talking about, as I said at the beginning, the synergy here is in capability. It's not necessarily in simultaneity. Now, I expect that if Axis launches, it's going to be up just as long as Chandra, if not longer. And so there will be an opportunity for simultaneity, but as motivating the mission, we don't strictly need that. So yes, for looking at individual variable sources like AGN, the very heart of the AGN, for that, maybe you do want some sort of simultaneity. But we're talking here about like kiloparsec scale impacts. And so, we don't expect changes there very rapidly. And so if there's a couple of years between the two missions, if Axis starts making, say, these mission line maps, and then Athena later goes and gets a spectrum from there, we don't expect time evolution on that time scale just because of the distances. Now, as to your other question, I mean, honestly, it's going to depend on the science case. Some of the science, as you can see from this scale bar here, you could probably accept a little bit more than 1 arcsecond. Could you accept 5 arcseconds? No, you can't, because again, if we go back to this scale, this is a 5 arcsecond map of this, which we get with Axis. So, I don't have a number for you. 1 arcsecond enables a whole bunch of science. And then it's a question for each of the individual science cases, what are the deltas around that? But we certainly, we're aiming for the highest resolution that we think we can propose and be successful with, just because we know that so much more science is enabled when you go to high resolution.
Any other questions? Should we move on?
And thank you.
Okay, so I'm going to tell you about high Z AGN surveys and dual AGN. I should say that I'm going to, an expert on dual AGN, but the high Z AGN stuff is from Nico Capoletti. And so let's start out with what we currently have, which is the deep field, Hubble Deep Field, and the Chandra Deep Field. And you can see all these beautiful galaxies that have been found in the deep field. And then of course with Chandra, you have all these point sources. And as you move out to the edge of the field, you can see that the PSF gets quite a bit worse. And even with the deep field of Chandra, we're still missing many of the early quasars that are found in serendipitous surveys, that are found in surveys using the optical, using the infrared. So we really need more depth and a larger survey area in the X-rays. So this is a 5 megasecond simulation with axis assuming this 1 arc second. So this, you can kind of see this A and B region. So the A region is on axis, the B region is 8 arc minutes off axis. So the upper right is the A is this region here is on axis, and this is off axis, 8 arc minutes. So you can see there's really very little difference. So it's because we have that great PSF going out to the edges of the field. Whereas if you look at with Chandra, you can see the 30 arc second bar. You really don't have that high angular resolution. So you lose out on your sensitivity. You can't detect your sources. So what is the important science that you get if you can really survey distant AGN? You get how did the first supermassive black holes form? How did they grow rapidly in the early universe? You can get a more complete census of growing supermassive black holes going back to the cosmic dawn and at the peak star formation epoch. And also, how does supermassive black hole accretion influence the growth of galaxies and large scale structure? So this particular plot here is showing a distant AGN that was detected. You can see right here the redshift 1120. And it's showing you the inferred black hole mass based on the stellar mass. And so this is showing you the redshift. You can see how sensitive JWST is, and you can see different X-ray flux limits. And what we're showing here is the 5 megasecond field that we showed in the previous slide, and then a 300 kilosecond field that's a little bit wider field, and then a wide field at 15 kilosecond. And you can see this orange line here. We could actually probe something like 1120 if we imagine that it starts with, at Z of 20 with maybe a 10 to the 5th mass black hole. We could detect the progenitor of this type of system that we're able to detect now out to much higher redshifts in a deep field or a medium field, and even in a wide field. So to put this in perspective, now this is the flux at 0.5 to 2 keV and at 2 to 10 keV, and you can see some of the other X-ray fields and see where axis is really helpful, particularly in the intermediate and deep, right? Athena will do better for wide fields. So it really is complementary, and this is showing you the deep and the intermediate. Now, I should say this depends a lot on delivering the 1 arc second PSF, and we'll talk more about that in the sort of instrumentation section. But to get these distant, very faint AGN, that's where axis really is complementary. And so what do you get from that? So this is assuming the 5 arc second PSF of Athena, so maybe these red points won't be quite as good. And we heard from Randall a couple of days ago saying perhaps the PSF will be somewhere between 5 and 10 arc seconds. But the general thing to note is that at high redshift, redshift 6 to 7, axis in the intermediate and the deep field will provide some additional constraints at the faint fluxes, so 10 to the 42 to 1043, and even at higher redshift, where we can perhaps constrain some theoretical models, redshift sort of 7 to 8. So these deep fields with high sensitivity will be really important. So, and then the final point, I won't go into this in great detail, is what we can really trace is the obscuration fraction with redshift. This is showing for a particular source, this would be the axis spectrum, and for a Compton-Dick AGN at fairly high redshift. And so axis can really help there too, because it's able to survey so many AGN and detect so many of them. Okay, so that was sort of the deep survey aspect, but there's a lot of science that we really get for free with axis. So as you can see, this is again a deep field. You can see all these galaxies, many of them are in groups, many of them are in mergers, particularly as you go to higher redshifts. And this is not an exact one-to-one match, but this is showing sort of an axis simulation. So you have all these different point sources, right? And the thing that you can do with axis, which you really could not do with Chandra, is actually have the resolution to resolve things on scales of 5 to 20 kiloparsec, depending on your redshift. And so you can see with Chandra, as you go off axis, right, this is where your PSF just blows up. But with axis, you can see you have that 1 arc second, and you really don't lose it going out all the way to 14 arc minutes off axis. So I think this is where more of my science comes in. I think this could really help us do the first study of dual AGN at higher redshifts. So we can detect those two, as these two get example galaxies here, as they're undergoing a merger, we know the obscuration increases. From nearby galaxies, we also will have a phase where we see them as dual AGN because the violent, merger is using gravitational torques to drive gas on the black hole. So we find these dual AGN. Because we're doing these survey fields repeatedly and we get so many AGN, we might be even able to detect the signature from black hole binaries, the periodic signature. And then Aaron mentioned gravitational wave counterparts. And then finally, the other important thing is because we're going to have this high resolution so far off axis, we can do really good astrometry. So there's various ideas about wandering AGN or recoiling AGN, but they're very hard to study, and the hard X-rays is great because it traces the AGN. So you really know, you can look at something detected with JWST or HST or whatever and see that it's actually offset from the nucleus. So axis really helps in all of those cases, because the astrometry, because of the spatial resolution. I think it's very complementary to Athena. And so all these different areas, I think it has unique characteristics. Right, just to highlight a nearby sort of dual AGN. So this is 5 arc seconds, right? So this is sort of the good PSF of Athena. It's possibly worse. So this is a nearby galaxy. And this is something that, years ago, I looked at with Chandra, and you can see these 2 hard X-ray sources. You actually have a dual AGN. We looked at it with the radio, it's very nearby. We looked at it with the VLA. We looked at it with a large optical telescope, Gemini, and we still didn't detect a secondary AGN. So we really need these X-rays for doing dual AGN studies. And you won't be able to do that at all with Athena. So this is just a larger survey we did with the great on-axis resolution of Chandra, and we found on the order of 10% are dual AGN in the X-rays of these X-ray selected AGN. So the last thing I want to leave you with, since I did this survey of dual AGN and X-rays, some smart people came together and said, okay, let's take the EAGLE simulations and run them through, because we can test how much X-ray emission we would expect, and do the simulations actually agree with observations of dual AGN. So this is from Rosas Rivera, and basically, so this is a single AGN, the number of major mergers where you detect an AGN on, and then I'm sorry, this is the purple is dual AGN, and then the brown is single AGN. And basically what they were saying is, you have some AGN variability over millions of years. So you don't detect all major mergers hosting AGN or dual AGN. But the interesting thing is, if you look at our survey from nearby galaxies, it's at 7%. So what they did is they looked at our sensitivity across the full sky. And so there's this huge offset between what simulations are showing, possibly because of the resolution. And so I think this is something that AXIS could really help with. One of the things they mentioned is that the peak dual AGN fraction from EAGLE should be about 2012 parsecs. So that's something you can resolve even as you get to higher redshifts. And then the final thing is just look at the ratio of single AGN to dual AGN. It's about a factor of 2. So you imagine all these AGN you detect that are in major mergers. With AXIS, you could actually look for a secondary source. So I will stop there. Thank you so much. Okay, questions? Okay, actually, Leah, why don't we have you get started, and then we'll have more time for questions after the science session.
Great. All right. Is
Use
this
this
the
if you
changer?
want, yeah.
Perfect. All right, great. So hi, thanks. I'm happy to be here to talk about potential AXIS contributions to stars and exoplanet science. Just for some background, I originally joined AXIS as like an ISM person, but I've been working on UV transits of exoplanets And as I started to kind of become more familiar with what people are looking for in atmospheric characterization, I started to realize like just how much AXIS could contribute in this field. But of course, I'm building on the work of many other people, and I would just like to acknowledge that. And sorry, they're all written in black at the bottom here. I forgot to change the color. Sorry. So yeah, so one of the major themes to come out of the decadal survey was worlds and suns in context. And we've identified several questions where AXIS can really start to contribute to this area. But to kind of summarize the broader question, I would say what we could potentially do with AXIS is answer the question, how does stellar activity affect the evolution and habitability of exoplanets? So in this figure on the right, it comes from a paper by Meadows and Barnes, where they're really talking about the ingredients for habitability of another planet. And in the upper left quadrant, I've circled some areas about stellar activity, understanding stellar age and rotation in magnetic fields, and even just the full SED of the star, which can affect the habitability or the development of life on another planet. So that's all circled in pink. And of course, this is really important and something that we can do in the X-ray, because this high energy characterization of stars and stellar activity is what tells us things like what is the EUV flux, what is the UV variability like, and those are the things that are affecting photochemistry in those atmospheres and those planets, as well as disequilibrium processes and potentially even stripping planets of their atmospheres. Speaking of stripping planets of their atmospheres, another area just right here, escape, is something that happens because, for instance, oh, I think some of my text is missing for some reason. All right, no worries. So in this little schematic here, you see like a planet with a stream of material coming out of it. So atmospheric escape is something that we know that happens to planets. So for instance, Mars lost its atmosphere through some form of escape. And it's something that we actually see, which I'll get to in a moment. So understanding how atmospheres can be sloughed off of exoplanets is really important. And it's suspected that a lot of that is in the X-ray and EUV. And so of course, looking at X-rays and stellar activity gives us a handle on how that affects planetary evolution. Another thing I'd like to point out, very nicely done in this schematic, is that the vast majority of exoplanets that are primed for atmospheric characterization are actually orbiting M dwarfs. And M dwarfs, oh my, there we go. M dwarfs, the reason it's great is because they're really small relative to the planet sizes we care about, so they have a stronger signal. They're about 10 times more abundant as well in the universe, and they're a lot more active. So these exoplanets that we want to characterize, where we think we could potentially start to find life or biomarkers, are actually also receiving 400 times more the X-ray radiance than we experience on Earth. So they're living in a completely different environment, and the X-rays are important to understand what exactly is happening with those planets. Okay, so where can AXIS really strongly contribute to these questions? Really, it comes down to this 1 arcsecond PSF over a wide field of view. So by using AXIS to look at things like young stellar clusters, and I just have an example of a open cluster from a Chandra survey to just showcase the vast number of point sources and why that PSF matters. But we can start to ask questions like, or answer them. How does stellar activity change with age? Can we look at that stellar activity and maybe monitor some of these stars to pin down the scatter and the age luminosity relationship? And can we really construct a history of flaring and activity for stars so that we can understand how they're affecting the evolution of the planets orbiting them? And I also want to come back to escape and why it's important to the exoplanet community. On the right here, you see a plot that shows the observed exoplanets that we have in terms of the exoplanet radius on the y-axis and their orbital period. And there's some general trends that have been observed. So one of them is this Neptunian desert. It's kind of the Pac-Man area in this graph, highlighted by the blue. And what we see there is a dearth of medium-sized close-in planets with thick hydrogen and helium atmospheres. The other thing we see is the radius gap right here. This is, it's a little hard to see, but there is actually a bimodal distribution in planet sizes as a function of orbital period. And that's believed that the small close-in planets have been stripped of their atmosphere and the further out ones are able to retain that atmosphere. So one of the key hypotheses in explaining some of these demographics is that their atmospheres were evaporated due to irradiation by the host star. But it's a super active area of research and there's many different ways to probe it. It's definitely something that we see happening in an action. So this is a direct observation of atmospheric escape that was very famous from Ehrenreich in 2015. And what they're actually observing here is Lyman alpha absorption using HST. And they see a strong transit in the blue wing of the Lyman alpha feature. And that's telling us is that there's a huge outflow of material. And on the right here, you see kind of a schematic of the velocity distribution of the material and where the planet is, and the stars over here in the center. And what's really interesting about this transit is that it's about 50% in terms of its transit depth, which was not something that people necessarily expected. And it's also not a planet that has a high estimated photoevaporative mass loss rate. So it is actually quite intriguing to see something like this. And of course, we could also potentially do this in the X-ray. So on the left, we have the discovery paper for an X-ray transit from HEAD19 which is a canonical hot Jupiter, just a Jupiter-sized planet orbiting its star really very closely. And this X-ray transit is several times the optical transit. And so what that is suggesting is that you're looking at a big puffy exosphere or material that's coming off of the planet. So that's, there is a poster on this, so I should point you to that. It's really cool. So there's some more analysis of this particular data set. But basically, we could do this observation with AXIS in to much higher signal to noise. Here's a simulated AXIS observation, and it's really just a novel way to measure planetary exospheres and escaping material. And something I just want to point out that this is a cool opportunity for AXIS, particularly because the less than 1 keV effective area is so much higher than the telescopes we have today. So it's about 20 times Chandra, just because Chandra has the ACES contaminant that's building up and kind of removing the soft X-ray sensitivity. And then in comparison to XMM Newton, it's 5 times the effective area in that energy band. And of course, the imaging resolution is really nice for getting rid of source confusion. So as an example, with HG189733, it was found in this paper as well that there actually appears to be a companion star. And then there's also another object in the background. So even at the time, I think that companion was not really well known. So it is important sometimes to have this resolution, but it also could potentially open up studies of transits of young planets and clusters where we think most of the photoevaporation happens. And I just want to point out that this is really frontier science and a lot could happen because again, just like GJ436b, like you could get something like a really large transit when you didn't expect it. So it's pretty exciting and it's just anything can happen and a particularly interesting and compelling case, I believe, for AXIS. Thanks.
Any questions? Since we're talking a little bit over time, why don't we just get started if you will. So we're going to switch now and talk more about the optics and the detectors and the mirror. So Will Zhang will be giving the first presentation. It's just forward, back, and then slide it on top.
Yes, please. So I'm going to spend a few minutes to tell you about the optics technology that is required to enable access. So this is my team. We call ourselves Next Generation Action Optics. So hopefully we'll make it in this generation. We are funded by Rose's APRA and Rose's SAT. Here, I think it's appropriate for me here to acknowledge, Paul Hertz, who is retiring from his, stepping down from his current position. I believe Paul actually was the person that made this SAT possible, which in turn makes this technology development possible in the last decade. So I think we should give, I in particular, give appreciation to all. So what's the mandate of my technology program? Basically, what we have three things we want to do. We want to develop a technology that has a point spread function that is either comparable to Chandra in the near term or better than Chandra's 0.5 arcsecond in the long run, hopefully by the end of this decade. And second thing is that we want to have a technology that's capable of making very lightweight mirrors so that we can actually launch a big area telescope into space. At least 10 times lighter, and currently most likely 30 times lighter, and possibly 50 times lighter. Okay. The third thing, equally important for us to be able to fund such a thing, we need the cost of these mirrors to be much lower, at least 10 times lower, possibly 20 times, likely 20 times lower, and possibly 30 times lower. Then, of course, there are many other characteristics we astronomers like and love, including field of view, bandwidth, the speed light, baffling, et cetera, et cetera. Some of this I will touch a little bit later on. So here is the paradigm as to how we built such a gigantic mirror assembly. So what we need to do is that we start with a lot of mirror segments, two of which are passing around. You will see what they look like, feel like, and they are very, very light, less than 1 millimeter thick. And its measure is about 4 inches by 4 inches. For those of you who use metric, it's about 100 millimeters by 100 millimeters. So we make a lot of this. In the case of access, we need about 150 mirror modules. We need to make about 18,000 mirror segments like the one you have in your hand. Okay, and then we integrate these modules into this what we call metal shells. Very much like a ring, very much like a Chandra shell, except it has 30 to 50 times more mirror collecting area. Okay, photon collecting area. And finally, you make all these rings together. Put them together, you form a gigantic mirror assembly, which weighs about a metric ton, very much like Chandra. So how do we make a mirror module? Okay, you first make a lot of mirror segments, and then you put them on this back plate. Right now it's just a placeholder. When we build a real mirror, of course we'll lightweight this thing, make it fancy, lightweight and stiff. And then you put one pair on top of this. You can see this mirror segments you hold on your hand has 4 little pumps on the back side. And these 4 little pumps are the ones support, are the things that support these mirror segments and bond them to this back plate. Okay, you finish the first pair, then you do the second pair, et cetera, et cetera. You repeat the process, typically somewhere between 20 to 30 times for each module. You end up with a module that had a lot of pairs co-aligned and bonded. Actually, we have a prototype module sitting here on the table with 5 pairs of mirrors aligned and bonded. And this module, actually, a moment later, I'll tell you, tests about 2.7 arcseconds HPD. Okay. So one point to remember here is that each pair of these mirror segments is independently aligned and bonded, one pair after another. So here's how we actually fabricate this 18,000 or so mirror segments for access. In the case of links, we would need something like 40,000 pieces. Okay. So what you do is that you piggyback on the most powerful industry, the semiconductor industry. You buy a block of single crystal silicon from them, which costs about anywhere between $1,000 and $8,000, depending on which day of the week or which week of the month you're buying it. It's a commodity. The price fluctuates enormously. So you buy a block and you cut it and you slice a piece off and you polish it and you grind away some of the material so that you can make it light and thin. And then you trim away the outer areas that are typically no good. And you end up with this mirror segment and with the 4 little things on the back, which will serve to support and bond the mirror. So here actually is actually a quantitative measure of 2 mirror segments we recently produced. This is the power spectral density, measuring the deviation between the mirror segment surface and its mathematical prescription. For Chandra mirror, this plotted in purple here, and this is the quality of Chandra mirror, and these 2 blue and red are for all practical purposes could just be the 2 mirrors that you are looking at. So basically, we are quite a bit better than Chandra. So we are about 2 times better than Chandra in terms of figure quality. And those mirrors are 30 times lighter and thinner, and 30 times cheaper, okay, in cost. So how do we know these optical measurements are reliable? You do an actually image requirement test. So we actually tested a pair, quite a few pairs of mirrors in the X-ray beam, and we get this about 2 years ago. We get about a 0.8 arcsecond HPD, high power diameter image. So this really says that our mirrors are as good as the optical measurements tell us. Okay. So after that, we stopped the single mirror pair testing process. We said we are going to integrate more pairs together to see to make a bigger and more realistic module. Okay. So here is what it looks like. So the single pair we tested, this is the 0.8 arcsecond actually image tested at 4.5 keV, by the way. If you tested this at 1 keV, the image would have been slightly better. Okay. So basically here is we plot this PSF versus time. And in the last few years, we drove down the mirror quality from about 5 arcseconds to 0.8 arcseconds. Actually, this mirror, the image has some distortion in it. So if we remove this tail, this mirror pair would have been probably 0.5 or 0.4 arcseconds. The reason there is this distortion is basically when you bound this mirror segments to the plate, you introduce the epoxy and the thermal disturbance, all kinds of things that cause the image quality to degrade. So this curve shows you the progress we made in the last few years. And this is what we project that we will be able to make in the next year or two. We first have the first 5-pair module we built and tested at about 2.7, 2.8 arcseconds. So I'm hoping that by the end of this year, okay, when we have to really finalize the angular resolution for access, we can build a module that tests at about 1 arcsecond. Okay. So this is our plan. So essentially, I have talked about this. So for the sake of time, I'm going to skip this. So this is a comparison in terms of different parameters between Chandra mirror and axis from TSF. We're talking about on axis. Chandra is 0.5 arcsecond, and axis is the 1 arcsecond. So off axis, 10 arc means off axis, Chandra is 10 arcseconds, axis is approximately 1.2 arcseconds. So effective area was quite a bit larger, and mirror assembly mass is about somewhere between 1/3 and 1/2 of Chandra's mass. This is how this enables you could to launch access on the Falcon 9 to almost an equatorial orbit. And mirror surface area, Chandra had a total area of 19 square meters, and access requires about 160 square meters. Okay. So this, of course, the whole thing is that in order for you to fit this within the $1 billion budget dollar budget of access, this mirror has to be cost less than $250 million. Okay. In comparison, Chandra's mirror, just a mirror alone, cost around $500 million in the 1990s. So this is, if you divide the number of dollars by the number of square meters, this thing is about 20 to 30 times cheaper in the case of access. And of course, that's exactly the factor we need to make access useful without breaking the bank. Here, I have a few questions answered, and in case you are too polite to ask. What's the single most important reason that these mirrors are so light? The reason is a single crystal silicon. So this is a real single crystal that has no internal stress. Okay, that is the key feature we are taking advantage of to make it very, very light and without warpage. Okay, and what's the reason why this mirror's figure is so much better than Chandra's? It's a combination of a special polishing process that we have developed, and also a use of commercially available equipment developed by the semiconductor industry. So basically, in the last 30-some years, the semiconductor industry has developed a very, very good polishing process to make a very, very high quality wafers, very large silicon wafers, very inexpensively. So we tap into that resource. Why is this mirror so much less expensive to produce? Two reasons: mass production and use of commercial materials and equipment. Okay. So what's the biggest hurdles you must overcome to make a module meeting or exceeding access requirement? Right now, we have two hurdles that we have to jump. One is the thermal control of the laboratory environment where the mirror segments are aligned and bounded and tested. Okay. Second is the epoxy shrinkage causing mirror figure distortion and misalignment. So literally, as we speak, we are struggling with this. And I believe that once we take care of the first one, we'll be very, very close to 1 arc-second, if not there already. And meanwhile, we had to struggle with the second one and to get us better than 1 arc-second. So fingers crossed, by the end of the year, we will know a lot more. Okay. The one last question that you have seen that access mirror has a terrifically good off-axis response. There are two reasons for that. One is access optical design is water Schwarzschild, which is much superior to the water line design that was used for Chandra. And equally important is access and mirror segments are much shorter in the optical axis direction. Okay, so for this mirror segment is only 100 millimeters. In the case of Chandra, is 840 some millimeters. That's the factor 8 that you will gain in off-axis quality, image quality. With that, thank you very much.
Are there questions? Go ahead.
It seems at least plausible that the cost of mass deployment will become irrelevant on this timescale. I understand that mass is a stand-in for other constraints, but if mass alone were eliminated as a constraint, are there places where you could make improvements on the present program?
Yes. So in order, there are two things. One is the aperture size, utilization efficiency. The other one is the mass. So yes, conceivably mass is not much a constraint in terms of launch cost. If the mirror is too thick, okay, then you reduce the effective area per open aperture. So there is a little penalty there, but not too much. So in other words, if we could double the mass of access mirror, it would make life a lot easier, actually.
Seems plausible to that.
Yeah, it is indeed. I think the launch cost. I think I believe it's going, as you do probably, is going to come down. So that's also something that we should take advantage of. Yeah.
So there's one question online from Mark Schattenberg about discussing the plan to mitigate the mirror distortion caused by coating stress.
Very, very good question. So the coating stress, I did not touch here. So because of this mirror so thin, when you coat a layer of iridium metal film on the mirror, it will distort the thing. That problem, we worried about it for a long, long time, but it turns out there's another industrial process called atomic layer deposition. And they, again, this is something developed by the semiconductor industry. What we have done in the past couple of years is we have coated a few mirrors that way. And basically, that process coats a mirror everywhere simultaneously in such a way that the front and back of the mirror stress balances out. You end up with a mirror that does not have stress. So if there is any distortion, we have not been able to measure. And that distortion is actually quite below 1 arc-second. So which is part of the reason why I did not talk about it. So maybe at 0.3 arc-second, that is a problem that we have to address. And we will worry about that when we get there. Yes, please.
So two questions about the final PSF you're going to be able to reach. Basically, so you went from the single segment to the 5 segment and found some things you didn't exactly understand that increased the noise or the PSF. And now, before you can build, you're going to have to go up to, was it 30 segments or 50 segments in a slice, and then you're going to have to align the meta shells. And then, are there parts of that process that give you pause at this point that we are, to reach that final 2 seconds by 2028? they're going to be a problem. 1 second, I can read it.
Yeah, there are many things that give me pause. So I think you see this process going from this is the hardest part, building this thing. Going from this to that really does not give me pause, and from that to that does not give me pause. In other words, I believe there are plenty of companies that will sign a fixed price contract with NASA to do these 2 steps. I don't believe there is a company that.
And there's no way they're going to introduce 1 arcsecond of tip tilt or any other misalignment in those 2 steps.
That's right. No. In other words, once this part, in terms of alignment, basically the alignment requirement here is defined by the field of view. Okay, you know, to measure the many arcseconds or many arcminutes even. So there is the optical alignment hereafter is very, very loose, because already you take care of the hard part. This is the true reflection system. Okay. And here, this part, yes, there are a lot of parameters that we have to study. Number one, the first one is how many layers should we build into each module? Okay. If you build 1 layer, you are half of the mass per unit area of Chandra. If you build 5 or 10, you are a factor of 10 lower than in mass than Chandra. So that's the kind of, it's a practical consideration one has to take into account. So currently we are baselining doing somewhere between 24 mirror segments. We will have to demonstrate that. So with that module we have built, we have not seen any degradation going from 1 pair to the 2nd pair to the 3rd pair, which was why I emphasized that there's no stack up error. Because when we show this way of doing things, immediately the first thing people think is, oh, you're going to have stack up error. By the time you get to the 10th layer, you don't have anything left. That's not true. So because we actually individually align and bound individual pair, the pairs under the current pair is just serving as a mechanical support. We do not use it or refer it for reference.
Okay, maybe let's
through the whole thing. Okay. All right, so I'm going to talk about the current concept for the focal plane design and also the technology that will make it possible. And I think I go forward with that. Okay. So there are 2 groups who are involved in developing the detector and focal planes for Axis. The first group I have listed here is from the MIT Cobley Institute, along with MIT Lincoln Lab. So this group is led by Mark Bouts, and I'm a member of this group. And then the second group is from Penn State in collaboration with Teledyne. This is currently led by Abe Falcone, who's also a member of the Axis team. So I do want to point out, as Will did, that our work for this is largely funded by NASA programs, including APRA and SAT programs. So if you took the time to read the concept study report that was delivered to the decadal in 2019, you may have noticed the somewhat unusual focal plane design. And so what I'm showing here on the right, this is just a rendering of Axis. It's actually a very simple design. So here Will's optics up here, or that's not gonna work. So you see Will's optics on the right, and then 9.5 meters away from that is a fixed imaging focal plane with a single imaging instrument. And in that initial concept study report, we actually had 2 technologies of detectors. We had what we call digital CCDs developed by MIT Lincoln Lab. And we had these hybrid CMOS devices, or HCDs, which are developed by Penn State. And so in the center of the array, we had this very fast, small detector. This was a CMOS surrounded by larger format, somewhat slower, but still fast digital CCDs. Now, the expectation is that we will down select to one of these technologies just to reduce the complexity. And that will likely happen by step 1 for this. Okay, so I will present the sort of the technology readiness of both of those, but this is the notional concept that we currently have for the focal plane. It's 2 detectors, either digital CCDs or hybrid CMOS devices in 4 detectors in a 2x2 array that you can see here. We're baselining the same field of view that we had before, which is 24 arc minutes on a side, or about 6 centimeters total. We can use 24 micron pixels with the 1 arc second or worse PSF that should sufficiently oversample things. So we're currently in a trade study to understand the effects of increasing the field of view to 36 arc minutes on a side. And so if we use that as the baseline range, then this is about 2 to 4 times Chandra's solid angle, Chandra ACES I solid angle. We need to go about 5 to 20 frames per second in order to avoid pile up. This is 16 to 70 times Chandra ACES frame rate. The other big difference from something like the Chandra ACES CCDs is that we need thicker depletion depth just to get better quantum efficiency at hard energies. And so that's we're baselining 100 microns, then that's about twice Chandra ACES. Other than that, the devices are not very different from what is currently flying, at least in terms of CCDs. Now we have ranges here, and we have trade studies that are underway, but these really need science drivers. So we've certainly shown you a lot of the science drivers already for Axis, but we're definitely inviting input from the community about what they want to see Axis do to help us design this focal plane in particular. Okay, so the status of the technology that we intend to implement on Axis. And so I have one slide here for the digital CCD technology status, and then another one for the hybrid CMOS devices. Now, these digital CCDs are so-called because they are CCD detectors, and they use the proven performance of what we would call conventional CCD detectors that have been flying on X-ray missions for almost 30 years now, but in a fast, low power CMOS compatible sensor. So this is a technology that's being developed right now by Lincoln Lab, which we are putting into an X-ray application. And so the recent work that we've done on this is to test a small format, small pixel device running very fast. When I say it's running very fast, we've actually run this up to 5 megahertz output. Typically, we run it at 2 or 2.5 megahertz output, and this is the pixel rate coming out of one output at 20 times the rate for Chandra ACES. And we've demonstrated the things that I'm showing in magenta here. So we've demonstrated low power performance. We've demonstrated low noise at these high rates, less than 3 electrons. We've demonstrated, let me move that, I'm not sure where that moved. We've demonstrated very good charge transfer efficiency and radiation tolerance with after bombarding it with high energy protons. I will point out, I don't know if it's actually been mentioned, but Axis will be in a low inclination, low Earth orbit, which is a very benign particle environment, not only a low non-X-ray background, but a very low radiation damage orbit. Nevertheless, we will have charge injection, which was used to great success on Suzaku to reduce the charge transfer inefficiency. And we've demonstrated devices that are 100 microns depletion, which meets our current requirement. And so right now in the lab at MIT, we have a larger format device with the same pixel size that we are going to baseline, and with 8 outputs. So a multiple output large format device, which we intend to run at rates up to 5 megahertz. And so by the step 1 deadline, we will have demonstrated 3 electrons noise at 5 frames per second, which meets the low end of that requirement. Okay, so the hybrid CMOS detectors likewise have been undergoing sort of parallel development and technical readiness demonstration. These HCDs, if you're not familiar with them and you didn't see Abe's talk in the last session, these are silicon detectors, and that way they're very similar to CCDs in the way they detect X-rays. However, the readout array is bonded to the detector rather than having this transfer across the device. And so you have readout electronics for each pixel, and this allows them to be very, very fast. So the group at Penn State has demonstrated the depletion thickness that we need with excellent quantum efficiency. These devices are inherently radiation hard because there is no charge transfer, and therefore there is no charge transfer inefficiency. They are also by design 4-sided buttable. They have pixel sizes and formats that meet the requirements that we have. As I mentioned, they are high speed, and they meet the 20 frame per second requirement. They're also inherently low power. And so as an example, to do something like what is currently done on the Swift XRT CCDs for about 8 watts, you would need 100 milliwatts to do that with a CMOS device like this. And they have proven flight heritage. They're just beginning to be flown on X-ray missions, but the water recovery X-ray rocket flight demonstrated one of these HCDs. And of course, again, if you saw Abe's talk, the plan is to use an even more advanced device on the Black Cat CubeSat. So the read noise remains a bit higher than we need, but that there are great strides being done by the Penn State group to reduce the read noise. Okay, so I think our intention is to put these slides public, so I don't intend that you should read this, but this has a lot more detail about the HCD stuff that I wanted to include. So feel free to look at that on your own time. And I don't have time to go into much more detail, but I did want to put up this list of references just to show you that we've been working both at MIT and Penn State pretty hard over the last few years to develop these detectors. And so feel free to dig into these references for additional information or ask me now, because that's my presentation. Casey, I can hand up first.
Oh, Eric, so the 2019 report had you following the curvature, the focal plane curvature that you need for the short shield optical prescription. How do you plan to do that with just, I mean, this is really cute, right? You can tilt each one. How do you plan to do that with 4?
That's right. So the plan is to do a single tilt, and it'll, the tilt will still be pretty similar, 0.2 millimeters from center to corner. For 24 arc minute, for the 24 arc minute field of view, it doesn't degrade the PSF by very much, as long as we're going for 1 arc second or worse PSF. I suspect that, and we haven't done this trade study.
That's my next question.
I suspect that when we get to the 36, and maybe Will can comment on this, the PSF in those outer regions will degrade significantly. On the other hand, we're still getting field of view for free, but I don't think we have a handle on exactly how quickly it degrades. And I think it depends on exactly how the telescope is designed.
The ideal focal surface is very close to a parabola. So to the extent that you are using 4 flat passes approximating that curvature, you're going to suffer some loss, but not a whole lot.
I'll also add that we have an approved APRA program to develop curved CCDs, curved X-ray CCDs in particular, but I don't expect that technology to be ready by 2028. Yeah, Paul.
I probably just missed it, but is there any requirement on energy resolution?
There is. I did not put it on here because it's pretty similar to Chandra. It's pretty similar to Chandra or Suzaku. So that does need a science driver, but the current requirements that we have are 70 EV at 0.3 keV and 150 EV at 6 keV. So very similar to missions that have flown even 20 years ago. 15 years ago.
Okay, so maybe let's go to our last speaker.
Yeah, this is the freaky pointer. Okay, so this is just the topic. I know that everybody wants keeping them from dinner, so I'll be really quick. So I'm Andy Patak. I'm the Goddard lead on Axis. So I have to admit it's partially my fault then that we have this really weird focal plane that Eric was just talking about in the report. But like he said, we wanted the design labs at Goddard to study both options, to give both options a fair shot at being the final focal plane. And that was the only way we could do that in a design lab run. So the next step is we need to get Goddard on board for this. I'm pretty sure there's a presentation I have to give on March 22nd, although I haven't gotten the formal invite for that yet, but it's obviously really important. You really can't do one of these mission proposals without either major industry support or a major institution like a NASA center supporting you. We're updating the science case. Anyone who's looked at the actually submitted Astro 2020 has already heard and can point out things that have changed that are out of necessity because we're on this abbreviated time scale. We have to have this done in the next year. Eric just mentioned some, for example, with the focal plane, we need to figure out, do we really want to push for the faster readout that we had in the proposal, original report, or should we go with 4 frames per second? But putting that in a positive light, 4 frames per second is still better than what you would get with a partial readout with ACES. So you will be able to do some, I think, exciting timing science. Like one of my favorite topics would be looking at nearby galaxies and monitoring X-ray binary populations, looking for things like the ULX pulsars, where you need roughly second or better timing. So we're going to be getting that, I think, no matter what we decide. But anyway, we need to settle on these, refine our science traceability matrix. And but I think the bottom line is that I don't think it's going to be that much of a change in the science that we propose. I think it's still going to be the exciting science case that we got, I think, effectively a nod for in the decadal survey report itself. We need to we need to settle on our science and technology teaming plans. The next slide will talk about the science side of that. We'll need to secure a spacecraft vendor. Goddard has well-established procedures for that. And then the other elephant in the room, besides getting to the optics, 1 arcsecond resolution, is the cost. And so during the initial study, there were 2 cost estimates that the team was proactively doing itself. One was automatic. So when you go through design lab runs at Goddard, they produce this thing called master equipment lists. You hand that to a cost modeler and they come back with a cost. So we did that and got an initial cost that showed we were in the box. We were under $1 billion. There's an office at Goddard whose main job it is to be like the gatekeeper. So they do independent costing. You're not allowed to negotiate or convince them that they're wrong or anything like that. They come back with a cost and that is what it is. And that office also said we were around $1 billion. And then finally, the decadal process included having this probe cost assessment team go through all of the probes that got headquarters funding, and they also agreed. So all 3 of these costs agreed that we were around $1 billion. Technically, we have more money now since the launch costs aren't included, but there's a question and answer website that I'm sure some of you have noticed, and on there it points out the fact for this probe call, and on that it points out that if you take inflation into account, this amounts to a whopping $50 million extra that the probes have. So that's not anything I think that's going to change our cost dynamic. So this is what I was getting at in terms of having an initial thought at having a science teaming plan. One thing that's unusual here is we have associate PIs. That's a new term that we just made up, but it's following NASA hierarchy. If you're familiar with how you have an administrator and a deputy and associate administrators, et cetera. So there's right now we have Rich Machowski as the PI, Aaron Carroll, you've heard a lot from at this meeting, is the deputy PI. A lot of the positions that we've laid out on here are open. And so there's 2 aspects here where we're taking the DEI impetus from the decadal survey very seriously. So one is what I just said, that these positions are open. We want to fill as many of these as we can with junior people. We need to, of course, maintain expertise. So the other aspect of how we're going to be doing this is a very strong mentoring approach. So like if you look down at the science working groups, there's going to be a lead and a deputy for each one. Either the lead or the deputy will be an early career person getting mentoring from the other. So we want to have this pro process also help develop the next generation of people with actual mission experience. Because that's a major dilemma right now. The perfect PI is somebody who's already led an explorer mission at least. And we all know it's an extremely short list of people. And I don't think NASA intends to only have 2 people eligible to apply to be the PI of a mission. So this is just a really rough schedule. Honestly, I just made this up off the top of my head, but you can just work backwards though. So we know we have to submit the proposal roughly March of next year. And so everything derived from that. So we get to get our support in place, get a spacecraft vendor. We're going to make them do as much as we can get away with. And then we have to form these science working groups. We don't have much time. I mean, usually all this would have been stretched out over 2 years for a typical Explorer proposal. But we were just told you only have a year. So it's going to be an abbreviated schedule, but that's why we're hoping as many people as possible want to get involved and join these science working groups and do the simulations that we're going to need. And then, there'll be a programmatic side to this, but I assume most of the people here are more interested in how we're going to develop the science case. And so since it's way past dinner time, except in Europe, I guess, you can scan this code and get to a Google form to sign up to be on different science teams. And if you have general questions that we didn't answer in this special session, there's an email address that we set up for you to send in questions. I'll stop there.
Okay, so are there other questions that people want to ask about science or anything else?